Okay, so this is trial by fire today. We're just engaging with large molecules and seeing if we can see general themes. The next reaction we're going to do is called kinase catalyzed phosphorylation. Phosphorylation means transfer of a phosphate group from ATP to something else, and the enzyme that catalyzes that happens to be called a kinase. That's not an important detail for today, but it will become important in the near future, and so I wanted you to have seen it. Take a look at that. Take a look at the starting materials and the products. I'm not going to give you any hints on this one. I want you to look at what has changed, what's different about the starting materials and the products. See if you can identify the nucleophile. See if you can identify the electrophile in the starting materials. See if you can identify the leaving group in the products. And then see, based on your comparison of the groups in the starting materials and in the products, particularly focusing on the phosphoryl or carbonyl groups, whether we've gone from level 1 to level 2 or whether we're downhill or uphill or neutral. Okay, take a few minutes and look at that. Try to use some of the tools that we just talked about for getting started. So that means, as you've seen, we'll use blue for the atom that gets attacked, pink for the oxygen that gets the negative charge after attack happens, and then green for the leaving group, which is all of this stuff. And that leaves as ADP. Good. And it was the, oops, there we go, alpha, beta, gamma phosphate group that got attacked. What was the nucleophile? The alcohol on glucose. Which one? There's so many. Yeah, that one. It turns out the enzyme guides the process for this reaction so that you modify this alcohol instead of any of the others. And then that alcohol gets attached here to what used to be, the gamma phosphoryl group of ATP. So we said the functional group over here is phosphoanhydride or pyrophosphate, either way. What is the functional group here? Phosphoester. Now that can be tricky. How did you recognize that as a phosphoester? You look at what, so the phosphate is bonded to not an OH but an OR. And it's not a carboxylate, it's basically an alcohol, okay? Good, questions about that, how we made that identification? Okay, so now phosphoanhydrades are level, level 1. Phosphoanhydrides are like carbon anhydrides, they're level 1. Phosphoesters are level 2, so this is downhill. Downhill means exothermic. Yeah, it would be a useful mnemonic device if downhill meant endo, because do for down, but that's actually not how it works. So exothermic meaning it releases energy, it goes downhill. Okay, good. This actually happens to be the first reaction in the metabolic pathway of glycolysis. This is what your body does to glucose to start extracting energy from it. This is the first reaction, and it's very, very downhill. Okay, got a couple of more. This one is how your body makes amide bonds. Oops, I think I just gave something away. This is how your body makes proteins. It links two amino acids together in proteins. It's tricky because the two reactive materials look extremely similar. So you're going to have to pay close attention to identify who the nucleophile was, who the electrophile was, and what the leaving group is. I will say there's a whole elaborate multi-subunit complex called the ribosome that makes this happen. And so even though looking at this, it may not immediately be clear why one is the nucleophile and the other is the electrophile. For now, just understand that the ribosome positions these two molecules in the right way to make what happens. Okay, so see if you can identify what the leaving group is, what the nucleophile is, what bond you formed, what kind of carbonyl or phosphoryl compound it is, and whether you've gone downhill. electrophile, okay. Aldehydes and ketones don't have any leaving group. So those are the two. But other than that, in general, the electrophile should have a leaving group. Okay. Anybody having a tough time getting started? Any hints, any questions that you're thinking? Ready to talk about it or need another minute? Oh, you're good? Okay. All right, so let's focus first on the bond in the product that is not present in the starting material. So looking at the products, what bond did we make here? Say it louder, I can't hear you. So between an NH and this carbonyl oxygen, what is the name of that functional group? Amide. Yep. It's like an ester, only it's nitrogen instead of oxygen. Okay? Now, over here to the left, which of your starting materials was the nucleophile? The glycyl tRNA, which atom in it? Yeah, that's the thing that now has a new bond. It didn't used to have a bond. So that means this is the group with a lone pair on it that does the attacking. Okay? Now, where is the leaving group? What left? Over here on the right, the thing that's called tRNA. So this is the 3' nucleotide of a big long tRNA. You may have heard about those before, you may not. Those are the carriers of amino acids that help with protein synthesis. So this tRNA abbreviation just means tons of other nucleotides in an RNA. Okay, so then let's highlight it over here. Here is the leaving group. That would make this the carbonyl carbon and this the carbonyl oxygen. Is that pretty clear? Any questions about how we made that decision? All right, what kind of carbonyl compound is this? Ester. Good. You know it's an ester. Why? Because it's an OR group attached. It's not a carboxylate. It's just an alcohol bonded to a carbon with no carbonyl group at this carbon. Good. So this is an ester. That's level what? Yeah, that's level 2. You said the product was amide. That's level what? Yeah, let's look back at our list. Amide is 3. The reason is the NHR minus leaving group is a poorer leaving group than an OR minus. The other reason is the NH is the nitrogen on the RNH group is a much better electron donor than the oxygen because nitrogen's less electronegative. That makes the amide carbonyl carbon really not very electron poor. And we're actually lucky that that's the case because that means the amides in our proteins are relatively stable are proteins that do all the work in our bodies, can last a long amount of time. Okay, so biology takes this ester and turns it into an amide, and that is downhill. Biology is great from going from level 2 to level 3. Biology is great at arranging things so getting the desired product is downhill. And that's kind of a beautiful thing, to arrange all the details in such order that things naturally flow the way you want them to go. All right, questions about that? All right, the last one I think you can probably do on your own. And so I'm going to leave that as an exercise for you to do after class. You can download this on the quiz and try that problem. I'll make sure it's in the key. We've talked now about why reactions happen. They happen when we go from something that's higher energy to something that's lower energy. We go downhill. And generally, if we want to go uphill, we have to couple that reaction to another reaction that goes downhill so that we can pay for it. All right? Now we want to get to the details of how they happen. What kinds of things go on to enable these kinds of reactions? You've already seen some of them in how we've talked today about ATP. For example, in our first reaction, we saw a phosphoanhydride become a phosphoester, level 1 to level 2, that's downhill. And I showed you how that process happened with attack of a nucleophile on an electrophilic phosphorus with electrons kicking up to give you this intermediate. And then, because there's a good leaving group on that intermediate, electrons kick down and the elimination occurs. How a reaction happens is its mechanism. And you've already seen mechanisms are usually strung together through very simple, what we would call elementary steps. You've seen one of these before. One is called addition. That is, nucleophile attacks carbonyl or phosphoryl group to give an intermediate. And then the second step was elimination, where negatively charged oxygen kicks off a good leaving group. Those are two fundamental mechanistic steps that we will see again and again and again in a lot of different contexts. There's a couple of other mechanistic steps that need to be in your toolbox for doing reactions. And so we're going to talk about these. We'll talk about them in a generic sense. And then we'll get more specific. Okay? Mechanistic toolbox. Item 1 is addition. We've just seen that. Nucleophile attacks a carbonyl carbon or a phosphoryl group at the carbonyl or at the carbon or the phosphorus, and we break the pi bond and electrons go out onto the oxygen, and that gives us an intermediate. I'm showing you the carbonyl version, but earlier today I showed you the phosphoryl version. Okay? So that's one fundamental mechanistic step. And with each of these fundamental mechanistic steps, you can understand them with the overall paradigm of HOMO attacks LUMO. The HOMO on the nucleophile, which in this case is lone pair electrons, attacks the LUMO on the electrophile, which is in this case the carbon-oxygen pi star. Okay? That's one you need to be very familiar with. Second is what I've just already summarized today, an elimination step. This can occur when you have a negatively charged oxygen in the same molecule and on an adjacent atom to a good leaving group. And when this happens, the electrons on the negatively charged carbon dump themselves into the carbon Y group sigma star, and the leaving group leaves, that creates or restores the carbon-oxygen pi bond and gives us this carbonyl containing product. Now, both of those things can happen. If they happen one after the other, if we do addition first and then elimination, we can get a substitution product overall. Where nucleophile attacks, we get a tetrahedral intermediate, then leaving group leaves. And so often people call the 1+2 punch, they'll call that nucleophilic acyl substitution. The acyl group is the carbonyl carbon and oxygen, and you're substituting the nucleophile for the Y group. Now, nucleophilic acyl substitution is not an elementary step, it's 2 steps, one after the other. Okay. Questions about those? That's review. A third really important mechanistic step is called, I will just call proton transfer. This can either be deprotonation or, I suppose, protonation of something. I mean, you can't protonate one thing without deprotonating another. I mean acid-base chemistry. So let me give you some simple examples of acid-base chemistry. A base, the HOMO is lone pair electrons on whatever the atom is, attacks the acid, and we're talking about the LUMO is the sigma star between the acidic hydrogen and whatever it's attached to. And we attack that sigma star and the sigma bond breaks. We have the base now bonded to a hydrogen, and then we now have A minus, which is the conjugate base of our acid. Sometimes biology needs to do proton transfer before you have a nucleophile that's ready to attack. Maybe you have a molecule HA that you want to be a nucleophile, but it's not negatively charged, so a base will remove the proton, then it becomes negatively charged, now it's a nucleophile. So you'll see again and again in biology, sometimes you got to do an acid-base step first to make a nucleophile. Another time where you will see acid-base chemistry will be one potential fate of the tetrahedral intermediate. We talked about this last time. Suppose you have this intermediate, here's the nucleophile, here's the Y group, here's the carbonyl carbon, here's the carbonyl oxygen, and suppose the Y group is not a good leaving group. And suppose the nucleophile isn't either, so there's really nothing that can happen here. Instead, what will often happen is we will protonate the carbonyl oxygen, what used to be the carbonyl oxygen, to get rid of its negative charge, and that will give us this, what I've called an addition product, where in place of the original carbon-oxygen pi bond, you've got the nucleophile and then the hydrogen from the acid. So if you do step 1 plus 3, we call that, well, I would just call that addition followed by protonation. Okay, so far, 3 simple steps: nucleophilic addition to a carbonyl or a phosphoryl group, elimination of a leaving group on what used to be a carbonyl carbon or a phosphoryl carbon. Let's see, what other things? Another important step, which we won't see too much in biochemistry, but which I think is important to talk about now, is something called direct substitution. This is where you have a nucleophile and then an sp3 hybridized carbon where that carbon is attached to a leaving group. We'll call it Y, since Y is our symbol for a leaving group. And in this case, the lone pairs on the nucleophile, the HOMO is the lone pairs on the nucleophilic atom, attack the LUMO, which for molecules like this, there's no carbonyl there, it's just the leaving group, carbon leaving group bond. The LUMO is the carbon leaving group pi star. So what happens here is direct substitution all in a single step. Nucleophile attacks the sigma star, the carbon leaving group sigma star. We form a new bond between the nucleophile and the sp3 carbon, and the leaving group leaves. That happens in biology, you won't see it a lot, and so I mention it here in case you have to deal with it, and so we can refer back to it if we need to. And that's basically it. Basically. Thank you. The dad joke, I didn't know I did. I'd call that 3 out of 10 on dad jokes, basically. Oh, I wanted to do one more proton transfer. This was a generic one. I said sometimes biology needs a nucleophile and it will remove a proton in order to get a nucleophile. Let me show you an example of that. Here's something you maybe didn't know. Protons, here is the carbonyl carbon. Here's the carbonyl oxygen, and this is the alpha carbon, the carbon that is adjacent to the carbonyl carbon. It turns out that protons that are adjacent to carbonyl carbons are more acidic than those that are not adjacent to carbonyl carbons. In fact, the pKa for being adjacent to a ketone is around 20. And normally, if there weren't a ketone there, the pKa for a sp3 hybridized CH bond would be around 50. So that's a dramatic increase in acidity. A base can remove this proton, and the reason it can remove that proton is because the corresponding conjugate base of your ketone acid is resonance stabilized. Here's the conjugate base, and here is its resonance structure. This molecule is called an enolate, and the negative charge on the enolate is delocalized in 2 places, the alpha carbon and the carbonyl oxygen. So nature will often remove alpha protons to generate enolates, and the reason nature wants to generate enolates is that these are good nucleophiles. All right, with those 4 simple steps, we could spend the rest of the class just doing, and I don't mean just today, but I mean until June. You guys know the day, right? I think June 16th is the last day. So you're marking it down, we're counting it down. Okay. What, you don't like spending time with me? I'm hurt. With these 4 simple elementary steps, we can work our way through basically most biological reactions. So we're going to start doing that. You have a mechanism handout that's here, and these are examples of reactions that occur in biology. And this isn't, I think this is maybe all of them. We won't talk about all of them today, obviously. And then on the back of your quiz, there's a chance for you to try some related things. We're clearly going to need most of the time next time to get through this, but I want to get started because once you practice it, you're going to feel like there's nothing you can't do. And this is important to get, it's an important level to get to before we start talking about metabolic reactions and how your body gets energy out of biomolecules. Okay, so let's take a look at that handout. I think I've got it somewhere. I thought I had it. Maybe not. All right, there we go. So, what we're going to do is look at starting materials and products. We're going to try to figure out what happened, and then we'll try to use what we know about elementary mechanistic steps to try to make it happen. Okay? So, your starting material is an aldehyde. This reaction is called hydrate formation. And so let's identify the carbonyl carbon of the aldehyde. Why are we, Somehow Notability has issues. All right, nope, it still has, whoa, that was bad. Wrong class. That's the right class, isn't it? Oh, all right. Well, whatever. Here we go. Carbonyl carbon, carbonyl oxygen. The leaving group is H. That's neither a good leaving group nor a good electron donor. So an aldehyde is level 1. Pretty electron poor at the carbonyl carbon. Let me look at the products, see if I can identify the leaving group and what used to be the carbonyl carbon, and what used to be the carbonyl oxygen. Now, tell me what happened in this reaction. What attacked the carbonyl carbon? Had to be water, right? It had to be the oxygen from water, right? And then what happened to the carbonyl oxygen? It got protonated. Presumably, otherwise, we should have seen a tetrahedral intermediate that looked like this, right? Okay. So let's see if we can figure out how that happened. Maybe I don't want to highlight the proton in the same color as I highlighted the nucleophile. Maybe we'll highlight the proton in orange. Okay. So, what likely is happening here is a deprotonation followed by nucleophilic attack followed by protonation. All right? Deprotonation followed by addition followed by protonation. You can do this stepwise if you want, or you could imagine it happening this way. Lone pair electrons on water act as the nucleophile and attack the carbonyl carbon, breaking the carbon oxygen pi star and moving electrons out onto the oxygen. At the same time, lone pair electrons on the carbonyl oxygen deprotonate another nearby water molecule, breaking that oxygen hydrogen bond at the same time as that water molecule steals a proton from that one. Okay, so that's one way that you can draw this mechanism. If you prefer to draw it out more sequentially, one way to do that would be this. Start with a water molecule. Have water deprotonate one water molecule to get a molecule of OH minus and a molecule of H3O plus. You're like, how likely is that to happen? Well, at pH 7 in water, it happens at about 10 to the 7 molar concentration. Then you can show the negatively charged oxygen attack the carbonyl carbon of your aldehyde to get a tetrahedral intermediate. And then you can show the negatively charged oxygen of the tetrahedral intermediate removing a proton from water to give you the product that's shown here. what we did, showing all of this at once or all of it like this, those are both fine. Yeah?
So I was thinking like the lone pairs on the water molecules for the HOMO, and then I was thinking the LUMO for the for the carbonyl.
Yes.
So what I did was you can't have the water molecule just attack right away. It has to be where you can.
Well, so that's a good question. How strong does the nucleophile need to be to attack the carbonyl carbon? I deal with that in my full-on organic chemistry class. I'm not going to do that here. Your intuition is correct. You do need to deprotonate the water first. And that's why I've arranged the mechanism either this way or this way. So if we do it this way, then yes, HOMO on the nucleophile, which is lone pairs on the OH minus, attacks the carbonyl carbon, attacks the pi star at the carbonyl carbon. You break the pi bond, you get a tetrahedral intermediate, and then HOMO lone pairs on oxygen attacks the LUMO of the acid, and then that gives you your product. We will see that enzymes frequently condense multiple protonation steps with addition or elimination steps. So enzymes will often speed up reactions by doing something like this. All right. Now, in the last couple of minutes, if you go to your quiz and go to the back page of your quiz, here is a reaction that is very similar to the hydrate formation reaction. You're looking at that and you're saying, no, it's not. It's way more complicated. Relax. It involves an aldehyde and an alcohol instead of an aldehyde and water. And it just so happens that the aldehyde and the alcohol are in the same molecule. So, see if you can figure out what's happening here. Give you a hint. Here's the carbonyl carbon. There's the carbonyl oxygen. There's the not a good leaving group aldehyde. And this OH is going to be your nucleophile. The water molecule is here to assist with any proton transfers you think are necessary to get from the starting material to the product. You can choose to draw this out stepwise or all at the same time. And it's fine. In the product, here is what used to be the carbonyl carbon. Here is what used to be the carbonyl oxygen. Here is the nucleophile. Here is the leaving group. And here is a proton I added to the carbonyl oxygen. All right, got any ideas how to start? How do I form the bond between the purple oxygen and the blue carbon? What does the attacking? Okay, you want to deprotonate it with what? So you want to use lone pairs on the water to deprotonate the alcohol. Okay, then what? Then you want lone pairs on the alcohol to attack the carbonyl carbon, breaking the pi bond. And then what? Yeah, and then reprotonate protonate the pink oxygen, by removing the orange proton from water. Now, if you wanted to draw that out, and that will work, the purple proton, which used to be on the alcohol, is now on the oxygen. If you wanted to do this stepwise, you would first show the OR group getting deprotonated by water. Then you would show the OR minus group attacking the carbonyl carbon. Then you would show the tetrahedral intermediate. And then you would show that negatively charged oxygen picking up a proton from hydronium. All right? We will continue on with this. If you want to get a head start and try some things between now and tomorrow, which you won't because you have an exam, go ahead and download the quiz and try some of these on the back page here. I know, it's fine if you don't. We'll just keep going. Good luck. May the force be with you.